So let's look at the second problem from the practice exam, which is 2.131. This deals with determining the component of a vector along a specified axis that's not one of our standard x, y, or z axes by taking a dot product with a unit vector along that axis. So here we have a pipe assembly. It consists of two parts, A, B, B, C. We have a junction at B. We have a force acting at C. In terms of what this will do to the actual structure, the component which is aligned or parallel to member CB will either compress this up into the fitting at B, or it will tend to pull it out of the fitting at B. So having that quantity of the magnitude of the force that acts along the axis defined by this member is an important kind of mechanical analysis quantity. So the key point, just using the same logic that I did last time, I guess there's two that we'll need to solve this problem. One is to find the component of some vector A along some axis that's defined by u hat, compute, and we'll just say AU, which it means the component of A along U is just going to be the dot product of vector A with unit vector U. Two, the idea that we can always decompose, kind of in a Pythagorean type sense, any vector A into any arbitrary perpendicular and parallel decomposition. So this is kind of, you can just think of it as a Pythagorean theorem type thing. So remember, if I kind of lose the vector notation and just talk about the magnitudes, what that means is that I can write a squared is a perp squared plus a parallel squared. So if I find a component which is parallel to a particular axis, which I'm going to be doing in this problem originally, so that's parallel, let me get it written there, I can solve for at least the magnitude of the perpendicular component by taking the square of the original vector magnitude and the parallel component and taking the square root. So we're going to need both of those formulas in this particular video. So in terms of how we will solve this, if you notice we're given the force, we want to find the component along an axis defined by segment BC. So what we need is a unit vector going, if we're going to project this onto this axis, we need UCB, and that's going to be equal to RCB divided by mag RCB. So it all begins again by just finding a position vector going from C to B. So in order to do that, let's get the individual components. You'll notice that in order to go to point B, we have these guiding lines. In X, we go out 3 units plus 3. In Y, we go over 4 units plus 4. Both of those are in the positive direction. And that point B is in the XY plane, so its Z coordinate is 0. In terms of point C, you'll notice we go out 3 plus 4 or 7 units in the positive X direction. We go over 4 plus 2 or 6 units in the Y direction. And once we're at that intersection of those two guiding lines, we go down 4 units, so minus 4. So recall that in order to get RCB, all that I need to do is to take each coordinate of B and subtract away the corresponding coordinate of C. So the X component will be 3 minus 7. The Y component will be 4 minus 6. And the Z component will be 0 minus 4, minus a negative 4, I should say. Be careful with your signs on this. And then once we simplify that, we'll compute what RCB is. So what is that? Well, it's going to be minus 4 minus 2 plus 4. And just ask yourself, do those signs of those components pass the sanity check? In order to go from C to B, do I have to go back into the page in X? Yeah, I go back 4 units. Do I have to go back towards the origin in Y? Yeah, I go back 2 units. That's why both of these are negative. However, in order to go from C to B, do I go up in the Z-axis? Yeah, that's why that is a positive 4. So in order to compute the magnitude, just square each component and take the square root of that. And if we do that, that will be minus 4 minus 2, 4 divided by the square root of 16 plus 4 plus 16. That's going to be the square root of 36. and that is just 6. So just simplifying this out, that unit vector will turn out to be minus 2/3, minus 1/3, and 2/3. So really, all that we need to do now in order to find the component of f along axis CB is to take f and take a dot product with UCB. F was given to us as having a magnitude of 33 in the x direction, minus 50 in the y direction, and 47 in the z direction. And we want to take that dot product with the unit vector that we just computed. And remember that the dot product is always just the product of the like components added together. So multiply the x components together, get that sum, multiply the y components together, get that sum, and multiply the z components together and get that sum. So you can compute this however you want. I'll go to MATLAB, and I'm just going to take 33 times minus 2/3, and I'm just showing more parentheses than I need to make my point of which each of my components are. So a lot of times when you enter things in that calculator, you don't necessarily do it the quickest way, just so you can easily make sure that whatever you wrote is what you're entering. So did we try to enter 33 times negative 2/3? Yes. Add that result to minus 50 times minus 1/3? Yes. Add the result to 47 times 2/3? Yes. So that comes out to be 26. So what that tells us is that the component of that specified force F along the axis CB, which aligns with pipe segment BC, is 26. And that, remember that the position vector had units of feet, the unit vector had units, its magnitude had units of feet, so the unit vector itself is unitless. So this will just take on the units of whatever F is, and we were told that F was in pounds. So this is 26 pounds. So that is for part A. So for part B, what do we need to do? Well, we use the same rule that we had up here. Remember that in terms of vectors, you can always write F as FCB plus FCB perpendicular. So this is the quantity that we want the magnitude of. Well, remember that going back to that triangle we drew and viewing it from a Pythagorean theorem point of view, in terms of magnitudes, the magnitude of F, which I'll just write as F without a vector, squared, equals FCB squared plus FCB parallel squared. So I can get what I want, which is FCB parallel squared, by taking the square root of F squared minus FCB squared. So I will just say here where F is the magnitude of that force vector, which is just going to be 33 squared plus minus 50 squared plus 47 squared. So what does that turn out to be? Let's compute over here. So it's going to be square root of 33 squared plus, I'm just going to be lazy and not show the minus 50, since when you square it, you get plus 50. And 47 squared, about to be 76. Wait, I'm going to carry all the precision that I computed now, just so I don't get a rounding error. So I can compute, actually, let me go back and define that as a variable F, just so I can easily put it into MATLAB. And what I want to do is take the square root of F squared minus 26 squared, and that will give me 71.57 pounds. So definitely know how to do that problem for your, and this is FCB perpendicular, and this is FCB. So make sure that you know how to do this problem for your upcoming exam. If you notice, there was a lot of overlap to the original problem that I did, because both involved kind of describing the geometry and coordinates. What I will probably do for the problem involving decomposition in 3 dimensions is to make it a problem where the geometry is described in angles instead.